Okay, good afternoon, everybody. I'm Rachit Manchanda, and today we are going to discuss embedded systems scenarios and their role in wireless sensor network. In the previous lectures, our experts has already discussed with you what is embedded system, their introductory part, and the real-time application of wireless sensor network. What I am going to discuss with you, I'm going to discuss with you their role in wireless sensor network, where embedded system use in wireless sensor network, and the most importantly, as a designer, as a researcher point of view, what kind of constraints I have to deal with when I use embedded system in a wireless sensor network. Okay, so that's what we are going to discuss. Secondly, what are the main challenges in the wireless sensor network? That's what I'm going to discuss with you, and how that challenge can be avoided with the help of this new emerging technology, this new emerging field that is compressive sensing. Might you heard of it? So that's what I'm going to discuss. I'm also going to discuss some mathematical part related to the compressive sensing, why it's so important, why we need it, and what's its role in the wireless sensor network. So on these topics today our session is going to have. So I'm just giving a basic introduction to the embedded system. What is embedded system? The most precise and the simple definition of embedded system is that any computer which is performing the computing task, and it is not a general purpose computer. That means it is not going to have a keyboard or the monitor. And obviously system, everything is going to be in a planned or an organized manner. There are some set of pre-programmed instructions which are going to perform an application specific task. Okay, and that application that I'm going to discuss with you is wireless sensor network. What is the role of embedded system in wireless sensor network? So we have those pre-programmed instructions which perform a particular specific task, or they can be the part of some larger system. Okay, so we have the software which is embedded into the hardware, and it have to perform one application specific task. Okay, okay, this is the basic block diagram of embedded system. I need it because I have to relate it with the architecture point of view of wireless sensor network. We have the sensors. There can be the variety of sensor. It depends upon in what scenario you are using your embedded system, in what real-time condition you are using your embedded system. There are different sensors. There are plenty of variety of categories of the sensors. For example, if you have to measure the pressure, use the bolometer. If you have to measure the thermocouple, you go for if you have to measure the temperature, you go for thermocouple. If you have to measure the variations, you use the piezoelectric. So it depends upon what kind of physical changes or the variations you are going to measure. Okay, and then after those physical conditions, physical changes has been measured, they have to be converted into the electrical form. Okay, that is the part of the sensors also, because they are the transducers. They convert it into the electrical form, and after that they have to be converted into the digital form. That's where analog to digital converters are coming into the picture, and they are very important. Why I'm saying because they are very important, because all the processing and the computation task, they are going to perform on that digital data, and that's where the processors are coming into the picture. Because suppose we have a black box, I'll give you some inputs, and I said I need that output. It's entirely up to you. That black box can be your DSP processors, they can be your FPGA, field programmable gate array, your CPLD, your PIC arm, whatever they can be, but they have to perform those computations. So that is the main discussion of today, that how that computation part, how that data part which is coming from the real time, that can be handled, and why it needs to be handled, why it has something to do with the wireless sensor network. This is the main key issue. Okay, and then we have the output interfaces. Basically I need to deal with the analog data again in the real time, they convert it. Okay, so these are the some important characteristics of embedded system. If I'll talk about any embedded system, the very first, that what I have already told you, they are application specific single function. Okay, application is the main priority, and the programs or the pre-programmed instructions are executed rapidly in order to perform one particular task. This is very important. Efficiency is a very important for any embedded system. Efficiency means I have to take care of the energy part, code size, execution time, weight and dimensions, and cost. I'll discuss this in detail when I'll discuss the architecture point of WSN, why it's so important. And embedded systems are typically designed in order to meet the real-time conditions. When we are measuring some real-time data, there they have to perform, there they have to monitor those changes in which particular environment they have been deployed. And embedded system, basically your sense, manipulate, and communicate. Okay, so we are going to discuss all these characteristics, how these characteristics can be incorporated with the your wireless sensor network. Okay, so there are plenty of examples of embedded system. You have heard about all these examples, so going into detail of everyone is not possible. So the most importantly, I'm going to discuss the embedded system role in wireless sensor network. Okay, so the firstly, where do wireless sensor network fit among the different wireless networks? We have the category of the wireless networks, and according to our need, according to our applications, we have the different kinds of networks. Any wireless network can be decided on the basis of its size and the range up to which it can communicate. Okay, on the basis of that, you can decide in what particular category of the sensor network you are dealing with. So we have first, I think you have heard of it, it's wireless wide area networks. Okay, under this category, your GSM, 3G, 4G, all these come under the category of your wireless wide area networks. I'm just discussing that where you can put your wireless sensor network. Okay, in which category you are going to put your WSN. That's what I'm discussing with you. And then we have WLAN, that is wireless local area networks. Okay, your desktops, they connect with the routers. Okay, Wi-Fi is one of the important example here, which is come under this category, and the most famous IEEE standard which it follows, it's 802.11. Okay, and the third is WMAN, that is wireless metropolitan area network. You are talking about city, 10-kilometer range. Okay, and here WiMAX is coming under this category with the IEEE standard 802.16. And here WPAN, which is personal area network. Okay, you are using it for yourself. This is in the context of some individual. Here you know that Bluetooth, Zigbee, ultra wideband, they all come under this category, and we have put WSN in this range, which is your personal area network. Okay, I'll show you this in my next slide, this one. Okay, so as you see, on the x-axis we have the data rate, and on the y-axis we have the range. Okay, so on the basis of that, the division has been done, and you see Zigbee and the Bluetooth, that is the category, that is the place where I'm putting my wireless sensor network nodes with the low range and with the low data rate. Okay, so that means everything which I'm going to discuss with you, yeah, everything which is related to the wireless sensor network, it's basically related to the low power, low data rate, or low communication range. Everything is low. So already the constraint part is there, that everything we have to keep it low, and still it is a very important network, wireless sensor network. We'll discuss it. Okay, so this is another diagram which is showing the same thing, that we are putting the WSN in the, okay, so we are putting WSN here. So this is basically, it is representing the low data rate, and obviously it is going to have the low cost, and also the one of the main important constraint which is related to WSN is the power consumption. It also needed to be the low. Why it is so important, the power consumption? Because we have a very small size of the sensor node, a very small size of the sensor node, and it is having a very small power related to it. Okay, very small power is going to relate with my sensor node, which keeping him alive. So if that power is going to be consumed, my sensor node is going to die. If one sensor node is die, I'm talking about a very huge network, wireless sensor network, where they are organized in order to do one particular task. If one sensor node die, entire network die. So it is very important that the power consumption is going to be low. Okay, so let's talk about WSN. Uh, the recent advances in micro electromechanical system. This is very important word, micro electromechanical system. That means both the electrical and the mechanical components on a single chip, and they are performing the task. And with the highly integrated digital electronics, the concepts of digital electronics are required here, because we have to convert our sensed data, which is in the analog form, into the digital form. They have led to the development of microsensors. Microsensors means sensors are going to have a very small size. They're going to have a very small size sensors, and these sensors are equipped with the data processing and communication capabilities. That's where your embedded system, the part of computation, that's where the part of your FPGA CPLD processors are coming into the picture, and they have to do that processing part, that the data that is sensor nodes are gathering from the real time, they needs to be processed. And because we are talking about a huge network here, all the sensor nodes are organized in a network, and they are going to perform a one specific application specific task. So that data which they have sensed, which they have processed, they have to communicate to their neighbor nodes. Okay, and the most important thing, lot of power is consumed when data is communicate. Okay, once sensor node have to process that data, sensor node has to apply all the mathematical operations onto it, and then it has to send that data to its neighboring node, so that finally the data can be transmitted to the base station, where it can be decompressed. We'll discuss it later. So power consumption is very important thing, which is related to my sensor node. It is the key thing, and the most of the research in the wireless sensor network has been done on this power consumption. Okay, how it can be reduced in an effective manner. So each node is basically given with the processing capabilities. This is the architecture point of view of wireless sensor network. This is the architecture of a single node. Okay, we have the sensing unit. Sensing unit, as you see, have the sensor and the analog to digital converter. Sensor is going to do all the sensing tasks. I have told you it depends upon in which environment you are developing your sensors. So according to that, that particular sensor is going to be used, and what physical conditions, what changes your sensor is going to be measured, they will be converted into the digital form by analog to digital converters, and that is also application specific. There are plenty of, not plenty of, there are analog to digital converters. You can use it RAM type or dual slope integrated type, counter type, successive approximation type. It depends upon what kind of application you are dealing with. And after that, that's where the processing unit, the computing unit, that is very important. It has to perform the computation task. It have to analyze that data which is coming from those sensor nodes. Okay, now that might be the possibility that after getting the data from the sensors, that might be the possibility that the redundant data is there. That might be the possibility that sensor nodes are gathering the same data, and that data you are transmitting to your processor. Each time they have to analyze that same data. So why sensor node has to waste their power in order to analyze the same data? Okay, one could think so that suppose these are the sensor nodes. Let's say we have the 4 sensor nodes. Okay, and all these sensor nodes are sending data to the one single node. Okay, I am talking about here heterogeneous environment. There are a lot of things related to wireless sensor network, so I'm just giving you the key concepts so that you can relate it. There are 2 types of environment in a wireless sensor network. One is homogeneous and heterogeneous. What is the difference between them? Otherwise, homogeneous, heterogeneous, it's also a very big topic. Homogeneous means the sensor nodes which you are deploying in a network, they all are having the same size, they have same range, same energy. Okay, but this is not the case with the heterogeneous. Some sensor nodes are with the more power, more range, more processing capabilities. So that's why I'm talking about the heterogeneous environment here. So let's say we have the routing protocol, we have the algorithm. Okay, so they are all are sending the data in the multi-host fashion to this one particular node, which is having a very high processing capability. Okay, this is called data aggregation. All the data which is coming from the different sensor nodes, we are gathering over here. Okay, so what they have to do, they have to just transmit the data. They do not have to process it. They have to just transmit the data to their neighboring nodes. Okay, and then finally the node which is having a very high processing capability, the node which is having a very high power, it is going to analyze and process all the data. Okay, so one could think like that. Another thing can be think of that in order to find out the pattern, that means in order to find out the duplicacy in the data, in order to find the redundancy in the data, that can also be found by applying the DSP functions over here, digital signal processing. There are plenty of functions over there. You can, for example, you can apply the autocorrelation function over here. It will give you the pattern among the data. Okay, and you can also separate the noise from the data, because you are dealing you are dealing with the real-time data. Sorry, you are dealing with the real-time data, so there might be the possibility the noise is also coming with your data. Okay, so another important thing, that after all the data which is aggregated over here, it can be reduced over here by applying the mathematical operations like mean. You can minimize it, you can average it. Then it is further transmitted to the next sensing node, which is also having the very high processing capability. This is called cluster head to cluster head transmission in a multi-hop fashion. Okay, I'm using the term cluster head. It means that among a huge network, for example, I have a lot of sensor nodes, and among that I'm making the cluster of, let's say, 5 nodes. Okay, and in that cluster I'm choosing the cluster head that is, let's say, that is the king, which is having a very high energy. Okay, in order to process the data, and now in the multi-hop fashion I'm transmitting that data to the next cluster head. Okay, and in this transmission the routing protocols are involved. It is not that much easy. First of all, you have to make the clusters, and there are the plenty of techniques. On the basis of that, clusters has been selected. After that, you have to choose the cluster head. One of the famous protocol, I think you heard of Leech protocol, which is basically used for cluster head selection, but that is for homogeneous network. And after that, you have to transmit the data to the next cluster head. So this is the one of the example that how the energy or the power can be saved in the wireless sensor network by cluster head to cluster head transmission. That means the transmission is taking place between those nodes which are having the high energy, and the rest of the nodes in the cluster are just transmitting their data to the node which is having high energy. So that's why the power and is a very important thing in a wireless sensor network, because everything is dependent on it. Once the node power has been die, entire sensor network is going to be die. And one could think of that I'll go and just change the battery, but it's not possible, because there are some locations where you cannot just reach and change the battery. For example, in the volcano, in order to measure the heat over there, the temperature over there, you cannot just go there and change the batteries all the time. Okay, so you have to use a very smart sensor network, a dynamic routing network which acts itself in the environment. Okay, so that's where the processing part is very important, because once the data part has been reduced, the most of the power is going to be consumed in communicating the data. So once you reduce the data, the communication part is going to be reduced, the power is going to be saved. Okay, and after that we have the transceiver. Transceivers are basically acting as both transmitter and the receiver, because sensor node have to transmit the data to their neighboring nodes, and they have to get the data from their neighboring nodes. That's why the trans receivers are used here. They're acting as both transmitter and receiver. The power unit on which the entire operation, the entire system, the entire network is working, a sensor node is working basically on, and on the sensor node the entire network is based, and the power generator is providing the power to the sensor node. We have the location finding system. If someone want to keep the track of the sensor nodes, they can have the location finding system. And mobilizer and actuator, they are basically acting as a controller. For example, if in the sensor network I have to split some fluid in the air, or I have to change the position of the lens on my sensor node. So they can be done with the help of this mobilizer and actuator. Okay, but the main unit is power unit. We have to save it, and I'm telling you again, most of the power is gone in the processing, and then lot of power is going to be consumed when you send that data to the neighboring nodes. A lot of work has been done onto this problem, onto this constraint. Uh, One solution I have discussed with you, anyways. Okay, there might be the diagram part is not very much clear to you, but I have already discussed this thing with you, that where we have a huge sensor network applications. Now, how can I put those applications? That can be put on the basis of that what kind of radio connectivity I'm using, what kind of routing I'm using. Okay, as you see in the diagram, I have already given you this example that cluster heads has been formed. Firstly, the cluster has been formed, and then the cluster has been formed. Okay, so here we have cluster has been formed, and these are the part of the cluster head, the nodes which are transmitting the data to their neighboring nodes in the multi-hop fashion, and that cluster head is transmitting the data to the next forwarding node. Okay, and then here we are using the dynamic routing. This is a called multi-hop radio connectivity. In the multi-hop fashion, you are transmitting the data to the data sink, and dynamic routing means it's a smart network. It is going to choose the path in order to reach to the data sink by itself. For example, some sensor node is die, or somehow it is going to have a very low energy, it is not able to transmit that data to the next neighboring node, then it will choose the search for the next path, that on by which path the data can be transmitted to the data sink. Okay, so this is the one category in which we put wireless sensor networks. Plenty of applications are basically put into these categories, because we have to deal with the WSN, we have to deploy the WSN in the real-time scenarios. Okay, where they have to be work smartly, so dynamic routing is needed over there. And the second category of the application is the where the single hop radio connectivity is there. There is no multi-hop connectivity, as you see in the diagram. Again, the cluster heads are there, but the node is just transmitting directly data to the cluster head. There is no multi-hop fashion, there is a single hop fashion in which they are transmitting the data. And there is static routing. Static routing means once by the algorithm you have decided the path, that by this path you have to transmit data to the data sink, they will only going to transmit the data through this path. They are not going to change the path according to their selves. Okay, so like in the I'll discuss one application related to this kind of category. Okay, in the home automation system, where you have deployed a lot of sensors. Okay, there this kind of static routing is there. So okay, these are the characteristics which I have already discussed with you, that in the first categories, sensor nodes acting as the repeaters. Okay, they are transmitting to the data to the next sensor nodes, to the neighboring nodes. Forwarding node supports the dynamic routing, means the main cluster heads is transmitting the data to the next forwarding node, and those nodes are basically supporting the dynamic routing. Okay, range is pretty high. If in this kind of category, radio links are measured in the thousands of meters, and forwarding nodes also support the data processing. That means while transmitting the data to the next nodes, they are going to perform the processing task. They are going to reduce the data. I give you one technique by which the data can be reduced, and how the data can be reduced in a more effective manner without affecting the originality of the data. Because you are reducing the data, there might be the possibility the originality of the data can be affected. You might lost the important information into the data. In order to avoid, you are trying to avoid the redundancy, but somehow you lose the main important information. So that's I'll discuss that technique with you in my next slides, that is compressive sensing, that how data can be effectively reduced. Okay, and this is the second characterizations of wireless sensor network, where sensor nodes are not supporting communications. They are not even going for the static routing. Range is pretty less in this case, 100 of meters, and forward nodes not supporting any data processing. So these are the two categories in which the applications, the entire applications or WSN has been placed. Okay, this is another cooperative and non-cooperative behavior. in the cooperative behavior, as the name suggests, that when the node transmitting the information on the behalf of another node, that means the nodes are cooperative in nature. Okay, nodes are transmitting the data in a multi-hop fashion. The things are taking place. One node is transmitting the data to the another node. Okay, that is the cooperative behavior of the nodes. And in the non-cooperative behavior, when a node handles only its own communication, okay, it's directly sending data to the base station or a sink. Okay, they are not having the multi-hop fashion over there. Applications of wireless sensor networks. Wireless sensor networks can be used in the military applications, where they can be used for monitoring the forces, battlefield surveillance, or in order to detect the nuclear or the chemical attacks. Wireless sensor nodes or the networks can be used in the military. In the environment, for the forest fire detection and the flood detection, that means sensor nodes have some threshold value, and if the water goes above that threshold value, they send an alarm to the user or the person who is sitting at the base station. And in the precision agriculture, there they have to keep the track of the nutritions of the plants, what minerals they needed, how much water they are needed. That's where they are used in the precision agriculture. In the health, for tracking and monitoring the patient's movement, and in the drug administration, they are basically used. In the home automation, home automation come under the second category of wireless sensor network, where there's static routing, there is no dynamic routing. And they can also be used in the commercial point of view, where environmental control in the industrial and office buildings, vehicle tracking and detections, and the traffic surveillance. So there are plenty of applications of wireless sensor network. Some of the applications, I think you have seen it, you've seen it in your daily life. So that's where the WSN is used. Okay, so one of the main challenge I have already discussed with you, that is the power consumption, and I have told you why the lot of power is going to be consumed. What is the main reason of that so much power is basically consumed in wireless sensor network when they have to transmit the data to their neighboring nodes, and then they have to process it. Obviously, we are dealing with the low cost network. We cannot basically use a very huge amount of batteries. It is going to increase the cost, because we are talking about at a very large scale. You cannot just use the high batteries, because we are not talking about just one sensor node or two sensor nodes. It's a very huge network in which the sensor nodes are deployed in order to perform one application specific task. So the low cost is a very important requirement here. So that's why we have to keep in the track so that the power cannot be consumed. Computation constraints, I've already told you that small sensor node have to process a lot of data, the data which they are gathering from the real time. Okay. And then communication, low data rates. I have told you where to put the WSN. They come under this category, personal area networks. Okay. So we have a very low data rates at which they are transmitting the data to their neighboring nodes. And these are not all the challenges. There are a lot more challenges which are related to the WSN also, but these are the main challenges basically which are related to the WSN. Researchers or the designers are basically working in order to increase the lifetime of the WSN, that in a particular field, in a particular environment, in a particular application, they work for the long time. Their lifetime, their network lifetime can be increased somehow with the different techniques. One technique which I have discussed with you, clustering algorithms, but there are a lot of flaws into it also. So anyways, so mainly why the power is consumed, I've told you most of the power is consumed in sensing, then you have to communicate, and then you have to process it. So power consumption is one of the main critical problem, and we have to find a solution for it. One of the technology I'm going to discuss with you. Okay, what is outlier in wireless sensor network? Okay, outlier means they are basically wireless sensor networks measuring something, and when they deviate from what you're trying to get from your wireless sensor network, they are measuring something, and what they are sensed, it is not that sensed part of the data, it is they deviate from their normal pattern. That means in a simple sense, you're getting the error, what you're trying to measure, and you're getting something else. that is basically come under the category of outlier. Outlier is a big category under which noise is coming. Due to the noise, my sense data can be affected. It's the normal pattern of the sense data can be affected. It can deviate. Another, there are events can occur. There are the malicious attack on the networks that can occur, which can affect my data. These are the potential sources of the outliers. I'm just telling you that noise is the very also play a very big role while you detect or send some data from the WSN. Okay, so okay, what are the network services can be provided? Compression and aggregation. Okay, both of them are basically use these network services in wireless sensor network. The first is to reduce the communication cost. We want the cost to be less because we are talking about a very big scale network over here, and we have to increase the reliability of data transfer. It should be protected. So both this data compression and aggregation is depend upon these two things. Okay, so data compression, what is that? That means you are compressing the data before transmitting it to the base. Okay, at the base station your data is decompressed, so I am just compressing the data before sending it mainly to the base station. Okay, I'm just trying to compress the data over here, the cluster head which I have selected, which I'm saying which is going to have a very high energy as compared to another nodes. Okay, I'm going to compress that data over here, because the benefit of compressing the data over here, the only benefit of compressing the data over here is that communication cost is going to reduce. Secondly, the power consumption is going to be reduced, because as I told you earlier that lot of power is consumed when you communicate the data, when you send the data to the other nodes. Okay, so compression is very important in WSN. Okay, and no information is going to be lost. You have to keep track of this thing, that while you are compressing, while you compress your data, you should kept in mind that original information is not going to be lost. Otherwise, when you decompress the data at the base station, you're not going to get the original information. If it lost somewhere here, so what's the point of compressing if you're not able to get the original data? Okay, so you have to keep track of this thing. And aggregation, data aggregation, I have already given you the example of the data aggregation, that data is collected through the multiple sensors. Okay, and it is combined over here. Okay, and then in the cluster based architecture form, it is transmitted to the next cluster, and then it is transmitted to the finally to the base station. Okay, why we have to select the clusters? One could think of that we can just transmit the data from one sensor node to another sensor node to another sensor node to another, and then at the last sensor node, it will going to process all the data. Okay, let's see if this is the scenario, what problem is going to come. Let's say this is my base station, or let's say this is sync. Here the decompression is going to occur. Here I'm going to get the original information. My user is sitting here, he is going to get the original information. So let's say this sensor node is transmitting the data to this sensor node. Okay, and what I'm saying that at the last this sensor node has to transmit the data to this. So let's say all the processing done over here, let's say all the processing handle will be here. Okay, because finally it has to transmit its data to this. Okay, so let's say if this sensor node is transmitting the data to this, now this sensor node has to send the information of this sensor node and also the information related to itself also. Now this sensor node has to send the information related to this, and then information related to itself also. Okay, so at the end, when finally you send the data over here, now this sensor node has the information of all these sensor nodes. Okay, and it have to process it. The traffic overload will occur here, or I can say traffic imbalancing, load imbalancing, traffic overload. This is load imbalancing. Okay, because this sensor node is to handle a lot of load. Once it transmitted, let's say it has a lot of energy. Once it transmitted to the base station, in the next time it is not able to transmit it again. Why? Because a lot of power is going to be consumed in order to handle the data of all these sensor nodes. Okay.
Sir, if from starting node, if you talk from starting node, it has transmitted information to the second node, then that node will become as a source and the next would be as a destination. So that we need to transfer the information of prior node also.
Because it is also sensing the information. It is also sensing, it has to process the information of its previous node also.
Yeah, that I have scanned. Now the second node will be source and the third one will be destination.
But if third one is destination, yeah. But this third one, when it transmits the data, the second node, which you are saying it is acting as a source now. Yeah. When it transmits the data to this third node, it has to handle the data of these two nodes also, the previous data also. Because at that time it is acting as a source, it is acting as a destination. It has the information of this sensing node also. Okay. And now this sensor node has to handle the information what it is having. This sensor node has to handle the information of both the previous two nodes. Okay. And then this sensor node has to handle the information of all these three nodes. I'm just discussing one scenario with you that one could think a scenario like this. Okay. But at the last, the node which is closer to the base station, normally this problem happens. The nodes closer to the base station, they normally get die due to they have to handle the huge amount of data which is coming from the backward. Anyways, so solution to this problem is cluster selections again. Okay. Introduction to digital signal processors. Why processors are so important? Because an embedded system is basically situated in an external environment where they have to sense the data, okay, and then they have to process it. They have to process the huge amount of data. So signal processors play very important role, and we are looking forward to compress our data at those sensor nodes. Okay, so let's see how that data can be compressed. This is the one of the example of the image sensor, the data that is sensed by the image sensor. I think you're already aware with the proximity sensors also. In your mobile, they will be near to your front camera or they will be near to your earplugs. So how proximity sensor works actually, when you take your phone near to your ears, they basically switch off the light in order to save the battery. Okay. So anyways, these are the examples of the sensors. What important features I need in digital signal processing? Okay, most of the DSP tasks requires the numeric computation. We have to perform a lot of computation. So they are capable of handling that huge amount of data. And obviously there is a requirement of high memory bandwidth, but we cannot use that such a high amount of memory because we are dealing with the micro sensors. They are having a very small size. So I cannot use that large memory or the bandwidth because it is going to increase the cost. And the real-time processing, obviously the processors are going to handle the real-time data. So a lot of things are depending upon the processors in the embedded system, that how they are going to process the data. And while processing the data, they must keep these things in mind, that the cost, the minimum usage of power should be there, the memory use should be minimum, and the development time should be minimum. Okay. So when I use this word data compression, we are talking about it, data compression. What is actually data compression is, and why it is so important in wireless sensor network, and why it is also important from the processor's point of view. Because the data compression is representation of the information source, is so that you can represent your information with the few number of bits. Okay, with the few number of measurements, you can represent your original data. And what is the concept why we are compressing this data? So that the communication part, the communication cost or the power can be reduced. Okay. And so this is the small diagram which is basically representing how the data can be compressed. The data can be compressed at the sensor nodes, okay, before sending them to the base station. Okay. First, the data is compressed at the sensor nodes with the energy efficient compression algorithm, which I'm going to discuss with you. There are plenty of data compression algorithms. I'm discussing with you one, which is compressive sensing. Okay. And that data is compressed so that now the processing part has been reduced. And then that data is transmitted to the next sensor nodes. And at those next sensor nodes and at the base station, we are basically decompress that data and we are going to get our original signal through that compressed version of the data. Okay, what is the basic criteria, comparison criteria for data compression algorithms? They can be analyzed and compare on these criteria. First is the compression performance, how your compression technique is performing. Second, the power is used when transmitting data without the compression. Let's say it is X, you are sending your data without compression. How much power is used, how much power they drain of the sensor node when you are not compressing the data. Okay, it is represented by X. And what is the power is used when you used your data compression algorithms. So these are the criteria. This is the simple criteria on the power of, on the basis of which you compare your data compression algorithms, and then you find out the net power saving, which is the subtraction of both. Okay, and suitability of data compression, it depends upon in which class of the data compression you're using. It is lossless or lossy. Okay, in the lossless compression, basically you are going to avoid the redundancy, duplicacy. Okay, you're just trying to remove that. You find the pattern, you find the duplicacy, and you're just trying to remove that duplicacy so that the sensor node has not to waste their power in order to process that duplicate data or the redundant data again and again. In the lossy, you actually remove the information part. Okay, which you think it's not relevant. Okay, that's what we are going to discuss, our lossy compression. So now this is the one of the very important technique, compressive sensing. What is compressive sensing? So before coming on to the compressive sensing, I have to discuss with you the concept of sampling. Okay, I think you're already aware with the concepts of sampling, what is sampling and what is Nyquist criteria. Okay, and one simple thing, that in order to reconstruct my data while performing the sampling, let's say I'm performing the sampling. Okay, let's say I have a one continuous time signal xt. Okay, so I'm taking the Fourier transform of this signal, and I'm making it band limited to the frequency fm. Okay, now this is my signal xt, and this is after the Fourier transform xl. Okay, now in order to convert it into the digital form, I'm just convolving it with the impulse train. I think you know that impulse train signal. Okay, so let's say I'm having an impulse train signal is this, and after taking its Fourier transform, it will be like this. Okay, so it will be like this with the this is my impulse train signal, and I am now convolving my this signal with this in order to do the sampling, in order to convert it into the digital form. Okay, so it will be like this. After convolving my signal xf with the impulse train, which is this fs summation n equals to minus infinity to n equals to infinity xf minus nfs. So the train of the signal I'm getting, it will be like this. So they kept repeating itself after a fixed interval of time, that is fs. So this train of signal I'm getting, now the main concept is that in order to reconstruct my original signal again, this is my original signal. Okay, in order to reconstruct it, what I use, I'm going to use a low pass filter. Okay, I'm going to convolve my this signal with the reconstruction filter, and that reconstruction filter is my low pass filter. And what that low pass filter do, let's say this is the transfer function of my low pass filter. What is going to do, this low pass filter just take this part of the sample. Now we are also having sample over here, we are also having a sample over here, and that low pass filter, when you convolve your this main signal, the train of the signal, the sampled version of the signal with your low pass filter, what it do, it will just take that part of the signal, and the rest part of the signal is going to be wasted, they needs to be neglected, and that is your Nyquist criteria. That means in order to reconstruct your signal, you need your sampling frequency double of your modulating frequency. That means you almost require double the samples which you are generating, and in order to reconstruct it again, you almost need double the samples of it so that you can get the original signal. That means lot of data is going to be wasted, and in order to store such a huge amount, lot of bandwidth requirement is there. Okay, you need lot of bandwidth. Okay, so what we are trying to do, we are trying to reconstruct this data at this rate, fs equals to fm. I know aliasing problem is going to be there, undersampling is there, but still with the help of the compressive sensing, with the help of some probabilistic or statistics functions, we are trying to recover this signal at this rate. Let's see how this is going to be possible. Okay, so in order to avoid this problem of sampling, the compressive sensing is coming into the picture, and the most important thing on which the compressive sensing work, it is basically your sparse recovery. You have to, this is the very important word, this is the key concept of compressive sensing. That means in order, first of all, you have to convert, you have to get the sparse signal. Okay, I'll discuss with you what is sparse signal. Sparsity means basically that is the compressed version of your data. Okay, you are compressing your data, and that is called sparse signal representation. That is the sparse domain of the signal, or in the more precise ways, you are getting the frequency domain of your signal. Okay, you are trying to convert your time domain signal into the frequency domain, and that is basically exploiting the sparsity of the signal. Okay, now how that time domain signal can be converted into a frequency domain? You have the Fourier transform, you have the wavelet transform, you have the plenty of transforms in order to exploit the sparsity of the signal. Okay, and from the researchers or the designer, this thing has not been done yet by any of the researcher. Always the transform they use, that is application specific. If you're dealing with the images, they use the wavelet transform. If you're dealing with some other application, they use some another transform in order to exploit the sparsity of the signal. But not a single transform is not used for all the application. It is always application specific. The sparsity, the spectrum you are getting. Okay, or another, and similarly in the wireless sensor network, not even a single routing protocol is applicable for all the applications. They are also application specific. Okay, so anyways, so the first thing, if I have to perform the compressive sensing, I have to exploit the sparsity of the signal. That sparsity means representing my signal with the few measurements. Okay, that is where the compression part is coming. You have to apply one transform. It will represent that huge amount of data with the fewer measurements. I'll show you how it is going to represent that huge amount of data with few measurements. Okay, and after getting those few measurements, now we have the compressed part of the data. I can transmit it to the next node. Means think like that. I have a one sensor node where that huge amount of data is coming from the other sensor nodes. Now I'm applying that compressive sensing to that one particular sensor node, which I'm saying it's a cluster head. Okay, there the data has been compressed. Now I'm sending it to the next cluster heads, finally sending it to my base station, and there I have to decompress it. That means I have to reconstruct it from the fewer measurements. Okay, how this is going to be possible? This is also called MASIC algorithm. I'll discuss it in my next slides. L1 minimization algorithm. Its tool is already available in MATLAB. Anyways, so we are taking the advantage of the sparsity of the signal. That's it. If you are not able to represent your signal in a sparse domain, nothing will going to be happen. Okay, the concept of compressive sensing is failed. So entire thing is depending on how you exploit the sparsity of the signal. Basically, how you get the spectrum of the signal, or in a more precise manner, how you're going to get the how you're going to represent your signal in the frequency domain. Okay, and that what I have already told you, compression can either be lossy or the lossless. Lossless means you are finding the statistical redundancy, identifying it, and you're trying to remove it. You are just avoiding the duplicate part of the data. No information loss is there. But lossy compression is a bit different. In the lossy compression, you are trying to remove the unnecessary part of the information which you think it's not important, or somehow it is not going to affect my original information. Okay, so Compressive sensing is my lossy kind of compression where we are exploiting the sparsity of the signal and then we are trying to reconstruct it with the fewer number of measurements. Okay. So this is the one of the example that what I have already discussed with you with the help of the diagram, that those who familiar with the Nyquist's rate, it states that in all the relevant information in the signal, the sampling rate must be at least twice the bandwidth of the signal. Consider a signal is the sum of several signals where the highest frequency sinusoid is 50 hertz. So in order to capture all the relevant information, it must be sampled at or above 100 hertz. Okay. So with the help of the compressed sensing, what we do, we're trying to represent it with the fewer samples and trying to perfectly recover it. In order to understand the concept of compressive sensing, first you should be aware with the matrix. You should know the algebra, mathematical algebra, which is related to matrix. That means you know the multiplication. You should know transpose, how to take the transpose. Okay. So these simple things you should know that before going into the compressive sensing. And I'll tell you the concept of compressive sensing with the help of matrix first. Then I'll come to the signals. Okay, how it works with the matrix. What I'm trying to say, how this thing is possible. Okay. Then you should know the signal processing basics. Very important, because without knowing the signal processing basics, you never know that how to exploit the sparsity of the signal. So you should have a deep knowledge of the transforms. Okay, you should know the Fourier transforms, wavelet transform, Adamant transform. There are plenty of transforms, so you should have a deep knowledge of them in order to exploit the sparsity of the signals. Because you cannot apply one single transform everywhere. I'll tell you why. Okay, and then you have to convert those time domain signals into the frequency domain. Okay, so you should know signal processing basics. Sparsity, I've already told you, it is the common term which is used in compressive sensing. What is that? It is basically sparse collection of the data has a very small number of non-zero values. That means a very huge amount of the data is basically represented with the few measurements, and the rest of the data you are taking in the mathematical terms is basically zeros. So you are taking the non-zero values which are very less. Okay. Compression technique. This is one of the example of the compression technique. I think you already heard it, JPEG. This is basically the compression which I'm going to discuss with you. It's a bit different from it, but this is the one of the example that you compress your images in or of files in your computer. Okay. So you probably run into the compression before. You compress your audio files, video files. Okay. So JPEG is a quite old and common standard. And there they use the DCT, that is your discrete cosine transform. Again, the sparsity is there. Okay. So its new version is there. They called it as JPEG 2000, and which is using the wavelet transform. So the transform is very important in order to know, in order to get the better compression. So what is spectrum estimation? That what I have already told you. That means spectrum means you are trying to get the frequency content of the signal. Again, I'm emphasizing on this thing again and again, just because this is the key part of compressive sensing. Without knowing the sparsity, without the prior knowledge of the transforms, there is no concepts of compressive sensing. Okay. Rest will be handled by the MATLAB scenarios. Okay. The tools are there, the commands are there. They will do rest of the things, but it's very important that you should know about the transforms first. So I'm going to take one of the example of the transform. Spectrum provides the identity and the signature to the signal. No other signal has the same spectrum. Okay, so spectrum is very important. In order to get the spectrum, we use the different transforms. Okay, information from the signal can be obtained directly or indirectly from the spectral content of the signal, for this we perform the spectrum estimation. Different methods are there in order to get the information from it. But firstly, we have to get the spectrum of the signal, that is the frequency content of the signal. Okay. This is the one of the example. You know that this is the most popular transform, which is your Fourier transform. And this is the function which is given for the Fourier transform in order to convert your time domain signal into the frequency domain. I think you know that. In order to change the domain of the signal from time domain to frequency domain, this is used. And the most important thing in this function is basically e raised to power minus j 2 pi ft. This is the thing which is converting the entire time domain signal into the frequency domain. This is called as forward kernel. So they are very important, and Fourier transform is is one of the very popular transform, but you cannot apply your Fourier transform for the non-stationary signals. You can apply it for your stationary signals where data is not changing, because Fourier transform works globally. Once you apply Fourier transform, it will act on the entire signal in a one particular instant of time. Okay, you cannot just check or analyze the separate part of the signals in different time spaces. You cannot check it. So this is the one of the disadvantage of Fourier transform, because in the real time scenario you are dealing with the non-stationary signals. Signals are going to be changed anytime. As I already told you, they can be affected by the outliers, the potential sources of errors, outliers, under which plenty of uh, things are coming, which by which the sensing data can be changed from its original or normal pattern. Okay. This is the example of the wavelet transform. Wavelet transform is pretty much used in compressive sensing. Okay, here tau is basically representing in this the motion of the window, and S is you representing the scaling of the window, and you can analyze the different parts of the signal by just changing the tau and S. This is its forward function, which is psi t minus tau by S, which is basically its forward function, and by changing the value of the tau and S, you can just analyze the different parts of the signal. So you should have the, I'm just taking the little bit examples of the transforms, but you should have a very prior knowledge of the transforms in order to know the compressive sensing, because this is the prime subject, a prime concept, that you have to apply the transform onto your data firstly and get the sparsity or exploit the sparsity of the signals. Okay, let's see what is the basic math behind the compressive sensing. Okay, this is very important. I'll try to understand you the concept of the compressive sensing with the help of this simple example. Okay, so these are the terms. The terms I'm using is exactly used everywhere in every paper, every research paper you study. They always use the same terms. Okay, they are not going to be changed. So I'm going to use the same terms. So whenever you study the compressive sensing, you find yourself familiar with this thing. Okay, so let's say we have any signal X. So here the signal which I'm going to represent it with X. This is my original information. Okay, which I'm going to compress it. And let's say this signal is represented in the time domain with the length of the signal is represented by N. Okay. If I'm not discussing the compressive sensing, I'll just take these N samples or the N length of the signal, and that's it. But in the compressive sensing, I'm trying to represent it with the fewer measurements. And let's say those fewer measurements is, I'm giving it represented with K. Okay, so we have an original signal, that is X, and that X signal is represented by the length of the samples, which is N. Okay, and that is the length of the signal, which is represented by capital N. And I'm trying to represent that signal with the few measurements, and let's say those few measurements are basically K. And I'm going to get this few measurement obviously after exploiting the sparsity of the signal. Here I have to apply what? The transform. Okay. So obviously this K is going to be less than N. That is the whole concept of compressive sensing. That's what we are trying to do. Okay. And with this fewer measurements, I'm trying to reconstruct it. Okay. So what is the math in between it before the reconstruction part? Okay. So we are taking a Y. Okay. This Y is actually going to represent our K measurements. Okay. So it is not important that one measurement is necessarily to have a one corresponding to the one single input. They can be changed because we are going to use the MATLAB functions over here. Okay. So, okay, let's take this example, how this thing is going to be happen. Okay. Let's say here in the example, we have representing X. With the X is basically my original information. Okay, let's say X is my original information. Okay, and it is represented by the length, that is N equals to 8. Okay, this X is basically represented my original information. This is my original information. Okay, here the length is given by N equals to 8. These are the 8 values I'm taking into the account. This I'm going the compressive sensing concept I'm just telling you with the simple linear algebra, that how this concept is actually working. Okay, and let's say I just require only 3 of them. Let's say I just require only 3 of them. That means I'm just compressing it and I'm trying to represent it with the fewer measurements. I need 3 of them, and it's very easy once you know that I need, let's say, first, second, or fifth. Okay, if so, I'm just applying here the matrix A. I think you know the multiplication part. Okay, y is equals to ax. Okay, y is equals to ax. Okay, and we have decided this A matrix by ourselves, let's say, because I know I required only 3 information. Okay, so by this help of the matrix A, I'm able to generate the information, the 3 information which I precisely needed, first, second, and fifth. Okay, as you see in the diagram. Okay, so this information has been generated. It is represented with the fewer measurements. Okay, but here we have already the prior knowledge of the information that I've already telling that I need first, second, and fifth. In this case, let's say I have already exploited the sparsity of my signal. Now the x which is represented, it is already in the sparse domain. Okay, and now you have to select the 3 samples from the original signal. Okay, first you have the original signal whose length is basically given by n equals to 8. Okay, and I said I just require only 3 of them, which is first, second, and fifth. It is very easy. By this A matrix, I can just easily get them. Y is equals to ax. That y is basically representing my k measurements. Okay, this y is represented my k measurements, which are my few measurements. Okay, now what I'm saying, it's very easy to know that once I have the prior knowledge of the information. Now I'm saying that this x is already, the sparsity has been exploited. Now my original signal is already, I'm representing with the few measurements. Okay, and now if I need the 3 of the samples, and if I'm using the same matrix A, it's not possible to get that particular samples. As you see, the y which is representing the information here, I'm getting 0, 0.18, and 0. But on the other hand, the information contains 0.18, 0.03, 0.11. Those 2 samples are missing. Are you getting this thing or not? Okay, so those 2 samples are basically missing. So that I need A like that, the entire entries should be filled. So A should be like that. It should have all the entries so that it can be multiplied with those sparse signals, the sparsity which have been exploited, so that the original information cannot be lost. So A should be like this. Okay, it is a Gaussian random variables, and it is a random function which is basically already in the MATLAB. Through that, this matrix has been generated. Now all the entries of the A has been filled, and when you multiply it with the sparsity of the signal, you are able to represent your original signal. Not entirely that original signal. Now 0.18 is represented by 0.2336, but somehow you are able to represent your original signal in the form of the fewer measurement. So the entire thing is dependent upon this A matrix. Okay, and that A matrix can easily be generated in your MATLAB by using the random function. It's already there. Okay, I'm not going into the detail of that particular function, but I think the key idea is pretty much clear to you, that in order to get those fewer measurements, okay, everything is dependent on A. You just multiplied it. Might be it is not able to represent it with that particular information, but it's somehow it's very near to it. Okay, but firstly, this 0, 0.18, 0.3, that means you have to exploit the sparsity of the signal, because the samples are basically 0 just because we have exploited the sparsity of the signal. Before that, we have applied the transform part. Okay, after that, the entire concept depends upon this A matrix. Okay, and it will going to give you the nearby values after multiplying to your sparse signal. So once this y has been generated, I needed it because now with the huge amount, that x which is having a length n equals to 8, with the y and with the help of A, I'm able to represent it with the 3 measurements. Okay, so if we see, we have some knowns and some unknown values, and we have some assumptions in the case of compressive sensing. What are the known values? Okay, in this 3x8 sensing matrix, A, this needs to be randomly generated, and we generated it. This can be easily generated by the MATLAB function. Random function is already available there. You can easily generate this matrix A. and 3 into 1 resulting output vector. That's why you are getting, because you know with these number of few measurements you are just representing it. So these things you know. Now you do not know the original values of x. It is changed because the fewer measurements, they are changed, they are not the same. I've already shown you that these are not 0.18, 0.3 and 0.11. They have been changed. These fewer measurements are different from the x. So x we unknown, x is unknown to us, the original values of the x. And what are the assumptions? The very important assumption is that 8 into 1 vector x which we are dealing, it's a sparse in nature. Okay, if it's not sparse, what we are trying to do, it's not going to work. And with the knowledge, how now the question is how we are going to figure out our original signal x, which is basically the values is whose values are pretty different to that values which we are measuring. So that's where the compressed sensing recovery algorithms are coming into the picture. And a popular method is L1 magic algorithm, okay, which basically based on L1 norm minimization. It's a MATLAB tool, it's already available there. You have to just give the command, and there is a lot of math is behind this. Okay, this is not just a simple topic which can be covered in half an hour. It will take around about 1.5 hours in order to explain just what is L1 minimization algorithm. Okay, so I'm not going to go into the detail of L1 minimization algorithm because I'm just discussing that how the data can be compressed and how the processor can be more effective in the WSN, because it's just the scenario of embedded system in the wireless sensor network. Okay, so but basically it takes a lot of time in order to explain what is this L1 magic algorithm. Okay, so this is the compressive sensing arrangement which I'm trying to discuss with you through the mathematics. The figure is actually showing the same arrangement what we are trying to do over here. As you see, first we have x, okay, and with the random projections, random projection means that is the matrix which I have represented with the A. When I have multiplied my x with it, I get the fewer measurements, that is basically y. Okay, and through the with the help of the satellites, they have been transmitted to the base station where this data is basically decompressed. Okay, and for decompression, what we have used the L1 norm minimization algorithm in order to get the original signal, that is x. Okay, this is the concept of basically compressive sensing, but it's just a glimpse of it. But it's a very huge discussion. Compressive sensing in a lot of fields it has been used. Okay, so this is another example related to the image, which is showing the compressive sensing theory. So entire compressive sensing, and the main importantly key issue in compressive sensing are measurement matrix design, that is the matrix A which we are talking about, and the signal recovery algorithm, the algorithm which is going through which I'm going to get my original signal. Okay, but everything is based on what? Sparsity. Okay, so that is a prior condition for the compressive sensing. In this diagram, this is the original image and it has been reconstructed again after. First of all, they have shown the wavelet coefficients. Okay, original megapixel image with the pixel values in the range 0 to 255, and we have just reduced it, and now this image is basically represented with the less number of coefficients that are called wavelet coefficients. As you see, the peaks are representing the main important part of the information, and the smaller values are basically we are just neglecting it. And again the measurement matrix design is coming, and then we have the L1 minimize algorithm, and after that we are going to get the original image. Okay, this is the algorithm for the compressive sensing. Okay, I'll discuss it with you. What's happening over here in the MATLAB coding form, what's actually done here. We have taken the original length of the signal that I've already told you. X is my original signal, and I'm taking here n equals to 256. It is basically representing my original length of the signal. And through this original length, in order to make it simple, what I have taken, I have just representing it with p equals to 5 already with the 5 number of peaks. Okay, because this signal is already in the time domain, I'm not discussing it in the because it's in the simple form n equals to 256. We are directly taking. If I take a signal like sine 2 pi ft, if this is the signal, there I can apply the time domain. I have to go into the frequency domain. There the transforms are actually coming into the picture. Okay, so I'm just taking the simple example. I'm just dealing the signal within the time domain. So I'm just representing it with the fewer peaks. Okay, so that's why we are directly representing with p equals to 5. That means the fewer measurements are already there. The sparsity part has been done over here already because it is in the time domain. Okay, so that's why no transform has been taken over here. So n equals to 256, it is represented by p equals to 5, and k equals to 64. That means for that n equals to 255, 256, 5 peaks we are taken from it, and we are going to represent with the k64 measurement values, and then from 256 to 64, and then we are trying to reconstruct it. Okay, so first of all, as you see in the generate signal with p randomly spread values, those peaks have been generated randomly, 5 peaks corresponding to that 256 values, and then we obtain the k measurements, that is basically y, in order to represent it with the fewer values. As you see, ra and dn, that is the random function which has been used here, and we have just put it the k and the n there. Okay, that means with that random probability function, I am trying to generate 64 measurements corresponding to the 256 values. Okay, and after generating the y, what the compressed sensing recovery has been done there. X naught is basically representing the, we are taking the inverse transpose of the y in order to generate x naught, and then the L1 minimization algorithm syntax has been applied over there in order to reconstruct the original signal. Okay, so it will be look like this. We have the 256 values, we represented it with 5 peaks, as I have told you. Okay, I'm just taking the 5 peaks, it doesn't mean the entire data has been represented with 5 peaks. Rest of the data we are taking zeros, and then we are trying to represent with the k measured values. Okay, these are the fewer measurements corresponding to those 256 values, and we are representing it with how much, 64 values. And after applying the reconstruction algorithm, the signal has been regenerated. Okay, and that is the recovered signal. Obviously some error is there, but this is the recovered signal. Okay, so the concepts of compressive sensing are basically used in the compressive data gathering. As the name suggests, what is compressive data gathering? That means the concepts of compressive sensing are now used in the wireless sensor network. What we have discussed is compressive sensing. Now what is compressive data gathering? That means we have the cluster heads. Okay, suppose we have this cluster head, we have taking this cluster heads, a small set of sensor nodes. Okay, and this is my base station. Let's say base station is here. Okay, so this is my cluster head. Now what is happening over here? The data is transmitting from this. The data has been transmitted from the sensor nodes to this cluster head. Okay, and at this cluster head, compression is taken place. Okay, so we are compressing the data over here. The concepts of compressive sensing has been applied over here, and now we have the another set where same thing is happening. Okay, and we are transmitting data from cluster head to cluster head, and then the data is transmitted to the base station. Okay, so ultimately at the cluster heads we are using the compressive sensing, and this whole setup is called as your compressive data gathering. In this fashion we are transmitting the data finally to the base station. Okay, so but this compressive data gathering, the compression is only possible if you are able to exploit the sparsity of the signal. Okay, so that's why I have first discussed with you the data aggregation, because you have to aggregate the data over here, and the important thing, you can apply the autocorrelation function over here, then you apply your compressive sensing, because through that autocorrelation function you can find out the pattern into the data. Okay, that might be the idea you can use. Okay, so okay, this is the some design where the sampling frequency, number of sensor nodes has been taken. Okay, so we are trying to represent my original signal with the 10 spikes, and number of measurements are taking as 80 and 220. And this is the entire mathematics behind the compressive sensing. Okay, so first of all, we are generate a random signal. Its mathematical function is given over here. Okay, this is the random signal we are generating. After that, we are adding the white Gaussian noise to it. So this is the one of the example where the entire mathematical part has been explained. Firstly, we are taking a random signal. So first we are generating one random signal. You can easily write it into the MATLAB. Okay, so secondly, we are just adding the white Gaussian noise. It is also the mathematically available there in the MATLAB. You can just easily add the Gaussian noise. Its function is given over there in the MATLAB. Okay. So after that, what we have taken, we are apply the autocorrelation function, so that in that data I can find out the pattern. Okay, I can distinguish the noise from my original data, and then in order to exploit the sparsity of the signal, I have applied the Fourier transform. All the functions which I have written there, they can be directly applicable, or they can be directly applied in the MATLAB, and you can see the waveforms. I'll show you. And then the generation of measurement matrix, the A matrix. On the basis of that, the fewer measurements have been generated. That's what I have shown you by the linear algebra. Okay, where y is equals to ax, we have multiplied my original signal with the A. That A is basically randomly generated, the value of m and n. Okay, m is basically the number of measurements you want in order to represent your signal. N is the original length of the signal. Like I have given you the example that 256 is the original length of the signal, and you want to represent with the 64. Okay, on the basis of that, you are generating A, and then you are reconstructing your original signal, and that signal can be reconstructed on the basis of the MATLAB function is there, that is L1 minimization algorithm. It is convex optical method. Its tool is available there. And if you want, you can calculate the average relative error. No need for the calculation of detection ratio. Average relative error, basically your true signal, which you have the data which coming to you, and after the compression and after the regeneration, what error is there, you can find out by this formulation. Okay, so this is the waveforms corresponding to that mathematical part of the data. First of all, this is the original signal we have generated in the MATLAB. I have given you the function also. After that, the white Gaussian noise, the green part which is added into the signal is basically the white Gaussian noise which has been added into the signal. And this is the autocorrelation function which has been applied to the signal in order to get the patterns. And after this is the FFT is applied in order to get the sparse domain of the signal. This is the sparsity of the signal. The peaks are basically representing the main important part of the information, and the rest part has been avoided. It is made 0. Okay, so okay, thank you. So